Hi, and welcome to an applied relative atomic mass calculation question. So it starts by saying gold and copper are used to make alloys, and it gives you the composition of a particular sample, obviously relating it to mass number, percentage abundance, and mass spectroscopy. So that sets the scene a little bit. So all you've got to do is calculate the relative atomic mass of copper due to one decimal place using the data for the two copper isotopes only. So looking at the information and just cross-referencing to the relevant two metals in the periodic table, gold and copper, you can see that the mass numbers match those of the two metals from the periodic table. So when we come down to the calculation, it says you must show your working. So you can see that there's 3 marks on offer over here. So you'll notice that I've put the isotopic mass times the percentage abundance for the two copper isotopes and the top part of the expression, the numerator, on the denominator on the bottom. I haven't put 100. Normally you'd put 100. So let's take a moment to think about why it's 51. So if we look at the two copper abundances, they add up to 51. I'm ignoring the 49 because the 49 is to do with gold. So it's only those two that I'm going to use. So that gives me 63.6, remembering that the question told me to do it to one decimal place. And a quick check with the actual relative atomic mass of copper in the periodic table reveals that it's actually more or less in the same area numerically. So that's a good way of checking whether your calculation is in the right place. If you'd put 100, obviously the calculated AR would be a lot lower, which would suggest that it's straying away from where it should be. So it should be in the region of 63.5 or close to that number. So that's a screenshot from my calculator, and you can see that by applying the one decimal place processing, that takes this number and rounds it to 63.6. So then it asks the percentage by mass. Now the percentage by mass is different to the percentage abundance. Now we don't know what the mass of this particular sample is, but the only thing that's to do with mass that we do have is the relative atomic mass, which in this case is 63.6. Now this is part 2, so it follows on from the previous question, so it's a good idea to take into account our previous calculation, 63.6. So we're going to account for copper's two isotopes present. So if I take the total of the percentage abundance and multiply it by my relative atomic mass, that gives me this number. Now this is quite a large number and maybe a little bit unexpected. What I'm trying to do here is get two proportions by mass of copper and gold. So if I do the same for the gold, I get these two numbers. So if my total of the two numbers is used, I can work out the percentage that each number represents. So by putting the total on the bottom and putting the number on the top and multiplying by 100, you can get 25% for copper and 75% for gold. If you put it through a calculator, you'll need to round slightly, but you will end up with 25% and 75%. Okay, hopefully that was a useful quick look at how this particular type of topic might be made more challenging. This particular one we're looking at right now, I would say, is definitely top end of A-star, if not slightly beyond A level in its demand. It's much more a mathematics type question really than a chemistry type one. Okay, as always, thanks for listening. Until next time, see you soon.